Have you ever picked up a rock and just wondered? I mean, every single one has a story to tell about an ancient world. You could be holding a lost river, a forgotten beach, or even a massive cataclysmic landslide. Today, we're going to learn the language to read those stories.
Just look at this thing. It's not just a rock, right? It's a 400 million-year-old story, a chapter from Earth's deep past. But how do we actually read it? How do we decipher what it's trying to tell us? Well, the secrets are written in a language that geologists call texture.
And no, texture is not just about how a rock feels in your hand, rough or smooth. It's way more than that. It's a whole set of clues, a physical record, left behind by the powerful forces of wind, water, and ice that shaped our planet millions of years ago. It really is the key to unlocking everything.
So, what is texture exactly? Well, it really just comes down to three fundamental things. First, the size of all the little individual bits and pieces in the rock. Second, their shape. Are they sharp or are they smooth? And finally, their arrangement, which is just how they all fit together. You can think of it like geological forensics.
All right, so this is where the fun begins. This is where we put on our detective hats. We're going to look at each of these textual clues one by one to see what stories they can tell us about an ancient world. So the first question we need to ask is all about power. Were we dealing with a lazy, slow-moving river or a raging mountain flood? The answer is hiding in our very first clue.
It all comes down to grain size. And honestly, it's a super simple concept, but the implications are huge. I mean, think about it. To move a massive boulder, you need some incredible force, right? Like a glacier or a flash flood. But to move some fine sand, all you need is the gentle lapping of waves on a beach. So the key takeaway here is this. Grain size is a direct measure of the energy of that ancient environment.
But the average size of the grains is only half the story. We also have to look at the variety of sizes in the mix. And this is a concept called sorting. It tells us whether the energy that moved all this sediment was steady and consistent, or if it was just totally chaotic and unpredictable. And what's so cool about this is how practical it is. This isn't just some abstract idea. Geologists out in the field use charts that look just like this one to figure out the sorting on the spot. Over on the left, you've got very well sorted. See how all the grains are pretty much the same size? And then on the right, you have poorly sorted, which is just a total jumble of big, small, and everything in between. And this difference tells a perfect story. Well-sorted sediment, with all those uniform grains, that points to a really stable environment. Like a beach, where waves have been washing back and forth for thousands of years, just sifting and sorting the sand. But poorly sorted sediment? Whoa, that's the signature of something sudden and violent, like a debris flow tearing down a mountain or a glacier just dumping its entire load of rocks, sand, and mud all at once. Okay, on to our next clue. We know about the energy of the environment now, but what about the journey itself? I mean, how far did these little pieces of rock travel before they finally came to a stop? To figure that out, we have to look at their shape. This little diagram shows us exactly what happens. When a rock first breaks off a mountain, the pieces are all sharp and angular, right? But as they travel, maybe tumbling down a river for hundreds of miles, those sharp edges get knocked off. They get banged up, abraded, and they become more and more rounded over time. So, if you find grains that are really, really round, you know they've had a long, tough journey, far from where they started. So we've looked at the individual grains, their size and their shape. But the last piece of the puzzle, the final bit of evidence, comes from how they were all put together in the final moments of that journey. This is what we call the rock's fabric. It's just the orientation and the packing of its grains. It's kind of like the geological version of a freeze-frame photo. It captures the exact way the sediment settled, and it can tell us some incredibly precise things about what was happening right at that moment. Okay, check this out. Just like logs floating down a river all tend to point in the same direction, long, flat pebbles will often get tilted and stacked up against each other by the current. It's a feature called imbrication, and they basically act like little fossilized weather vanes, pointing in the exact direction the ancient river was flowing. It's an ancient compass, locked right there in the stone. The fabric can also tell us what was carrying the sediment. Look at the left here, in what we call a grain-supported rock. All the pebbles are touching each other. This tells you a current, probably water, was strong enough to wash away all the fine mud between them. But on the right, in a matrix-supported rock, you see the pebbles are kind of floating in the sea of mud. That is the classic sign of a messy, chaotic debris flow, where everything just got dumped together in a big sludge.
Okay, we have all of our clues. Grain size tells us about energy. Roundness tells us about the travel distance. And fabric tells us about those final moments when everything's settled. So now it's time to put it all together and reconstruct the scene.
Because here's the magic part. When you combine all of these clues, you find that different ancient environments leave behind their own unique and unmistakable textural fingerprints. The pieces of the puzzle suddenly snap together to form a really clear picture.
And this table right here basically shows us the solution. Let's take a beach. What's its fingerprint? Well, the grains are sand-sized, they're well-sorted and well-rounded because of all that constant wave action. Now, what about a river? The sorting is a bit more moderate, the grains aren't quite as rounded, and they might even be imbricated, pointing downstream. And a debris flow? Oh, that's a whole different beast. It's a chaotic mix of everything from boulders to clay. It's very poorly sorted, and you've got angular fragments just floating in a mud matrix. See? Each environment leaves a totally different signature. Now, reading these stories is absolutely fascinating, but it's not just an academic exercise. It's not just for fun. Understanding a rock's texture has huge, huge implications for our modern world, from finding resources we need every day to just understanding our planet better. To put it as simply as I can, for so many practical purposes, texture is destiny. It controls the physical properties of the rock that we actually rely on every single day. Texture determines two absolutely crucial properties. The first is porosity, which is just the amount of empty space in a rock. The second is permeability, which is how well connected all of those empty spaces are. The easiest way to think about it is this. Porosity is the size of the water tank, and permeability is the size of the pipes connecting everything together. And here is why this matters so much. A rock that's made of that well-sorted, well-rounded sand, remember that ancient beach we identified? It's going to have tons of space between the grains. That means it has high porosity. And those spaces are also really well connected, which gives it high permeability. And when you get that exact combination, high porosity plus high permeability, you have a reservoir rock. That's the kind of rock that holds our planet's groundwater, our oil, and our natural gas. All that geological detective work leads us directly to these vital resources. So, the next time you're out for a walk, just pick up a stone. Look at it. Really look at it. Is it made of sand or is it made of pebbles? Are the grains all one size or a total jumble? Are they sharp and angular or smooth and rounded? Because now you know the language. Every single rock tells a story. What will you discover?